Have you ever stopped to think about what the secret ingredient is to, well, pretty much everything? Today, we are diving into the quiet architect of our entire world. It's an element that connects the fuel in our cars, the diamonds in a ring, and the very cells that make you, you. Let's get into it.
So I want you to really think about that for a second. I mean, on the surface, these things could not be more different, right? One is squishy, living life itself. One is the hardest substance we know, and the other is pure energy, ready to burn. So what on earth is the connection?
Yep, carbon. It all comes back to carbon. This single, unbelievably versatile element is the fundamental building block for all of them. It's the absolute star of a chemical story that explains the magic behind our world and even us.
So just how important is carbon, really? Well, let's start with its biggest claim to fame, being the fundamental element of all life as we know it. Now this number, this is where things get really fascinating. This is the amount of carbon found in the Earth's crust, just a teeny tiny fraction. So despite being the backbone of all life, it's incredibly scarce. How can something so rare be so central to everything? Well, the secret isn't in how much of it there is, but in its chemistry.
To really get to the bottom of carbon's magic, we have to shrink ourselves down, way down to the atomic level. And it all kicks off with a little problem, you could even call it a dilemma, that every single carbon atom has to solve just to become stable.
Okay, so here's the puzzle. Every carbon atom has 4 electrons in its outer shell, but to be stable and happy, it wants a full shell of 8. Now, it could try to gain 4 more electrons, but its nucleus just isn't strong enough to pull that off. Or it could try to give away all 4, but that takes a massive amount of energy. So what does it do? It comes up with this totally ingenious solution. It doesn't gain or lose, it shares. And this act of sharing creates what we call a covalent bond. It's beautiful, really. Instead of one atom just stealing an electron from another, 2 atoms decide to cooperate. They each put an electron into the middle, forming a shared pair that orbits both of them. It basically glues them together and lets both atoms feel like they have a full, stable outer shell. Let's look at the absolute simplest example. Hydrogen. A hydrogen atom has 1 electron, but it wants 2 to be stable. So, 2 hydrogen atoms get together, they each share their 1 electron, and voila, you get a super stable H2 molecule. This simple idea, this principle of sharing, is exactly what carbon is about to use to build incredible complexity.
And here it is in action. This is methane. It's the main component of natural gas. You've got 1 carbon atom in the middle, and it's sharing its 4 outer electrons with 4 different hydrogen atoms. The result? A perfectly stable molecule where everybody is happy. Carbon gets to feel like it has 8 electrons, and each hydrogen gets to feel like it has 2. It's a win-win.
Now, this ability to form 4 stable bonds is just the beginning. This is what unlocks carbon's 2 incredible superpowers, and these are the keys to its insane versatility. So it's this combination that's so crucial. On the right, you have tetravalency. That's just a fancy word for its ability to form 4 bonds, like we just saw with methane. But on the left, now that is the real game changer, catenation. This is carbon's unique, almost magical ability to form strong, stable bonds with other carbon atoms, creating chains that can be almost infinitely long. You know, the source material puts it perfectly. It says the carbon-carbon bond is just incredibly strong and stable. And that strength is what allows it to form millions of different compounds. No other element in the periodic table can link up with itself quite like carbon can. So when you have these 2 superpowers, bonding in 4 directions and linking up with itself, carbon basically becomes the ultimate Lego brick of chemistry. It can build an endless variety of amazing structures. First off, carbon atoms can just link up to form these long, straight chains. What you're looking at here is hexane, a chain of 6 carbon atoms. This stuff is a key component of gasoline. It's a perfect example of catenation just doing its thing. But life isn't always a straight line, right? Carbon can also form branch chains. So what you're seeing here are 2 different molecules that have the exact same chemical formula, same parts in the box, but they have totally different structures. We call these isomers. And this ability to rearrange the same pieces into different shapes, well, that's a huge source of chemical diversity. And if that wasn't enough, the ends of a carbon chain can actually loop back and connect to form these super stable rings, like this cyclohexane molecule here. So think about it. You have straight chains, branch chains, and rings. This incredible structural flexibility is why there are more known carbon compounds than compounds of all the other elements combined.
It's just wild.
Okay, let's bring this all down from the molecular level to something we literally all do every day: cleaning. It turns out the very structure of these amazing carbon compounds explains the magic behind soap.
A soap molecule is like a master of disguise. It's got two different ends. It has a long carbon tail that absolutely hates water but loves oil and grease. And it has a different kind of head that loves water. So when you're washing your hands, the oil-loving tails dive in and grab onto any dirt or grease. Meanwhile, the water-loving heads all face outward, forming this perfect little sphere you see here called a micelle. This structure literally traps the dirt so it can be easily washed away by water. It is pure chemical genius. But do you ever notice how sometimes soap just doesn't work as well? Especially in what we call hard water. Well, that's because the minerals in hard water react with soap and form that gross, insoluble gunk we call soap scum. Detergents, which are also carbon-based but have a slightly different structure, were literally invented to solve this exact problem. They don't form scum, so they stay effective no matter how hard the water is. Pretty clever.
So, let's just recap the whole magical journey of carbon. It starts with a simple atomic problem that forces it to share electrons, creating those super strong covalent bonds. That sharing gives it two superpowers, linking with itself and bonding in 4 directions. And those powers allow it to form a nearly infinite variety of chains, branches, and rings, which in turn build the complex, beautiful, and delicious world we all live in.
It really is an incredible story, isn't it? From one simple, fundamental need, an atom's desperate quest for stability, the entire complexity of life and all the matter around us is born. It really makes you wonder, right? What other profound, complex realities are built on top of such simple, elegant rules? I hope this gave you something to chew on. Thanks so much for joining me.